Welcome, folks. Good morning. I'm glad to see some very bushy-eyed people here, especially after last night. Did everyone get up too much last night? Good night? Bit dusty in the morning? Yeah. Cool. So, welcome to the talk. This is a little bit of a little talk that I've been thinking about for a few months now. Let's get right into it. So, in here, we're going to talk a lot about threading. So, fair warning, this is a very, very engineering-heavy talk. There is, like, maybe a few diagrams, and the rest is literally code. So, if you're ready for a 9 a.m. start, let's go. So, we're going to go through a few things. So, we're going to go through what Unreal has to offer in terms of threading systems, like runnable threads, the task system, task graph, the primitives, so like atomics, locks, all of the stuff they're used to in other engines, and maybe even in the engine that we're using right now. And a lot of thread safety gotchas and all that stuff, and like talking about multi-threading new objects and maybe a bit of blueprints, which is going to be very, very spicy. And then we go into a little bit about debugging threads and profiling. And then, because I'm a big fan of demos, we've got a little special thing for you later on. Some of you might know who I am. So I'm Alex Stevens. I used to be one of the evangelists in the region for Epic Games up until a couple of years ago, where I went full-time indie. And now I'm actually a senior engineer at Gameloft. So I work on the tech team between two projects that we're working on, which is pretty cool. Basically, a part of my job there is to basically look at a lot of the the low-level tech side of things and build systems and all that stuff for the rest of the teams to be able to use and look at optimization and a lot of other things. In the past, I've done a lot of consulting and contracting for studios, and including when I was at Epic, I would literally get injected into a studio and help them ship and do stuff like that. So, and one of my big fashions is, if you remember the talk from last year, is virtual reality. So with virtual reality, there's a lot of opportunities to learn to optimize, because you're definitely on a platform that is very cut at the knees, especially when you're on native Quest. So being a mobile VR platform, it's pretty hard to develop for. So you tend to learn a lot about optimization in UE, but I love it. So, all right. So why are we talking about threading today? Now, there's a couple of reasons. Well, I think a couple of engines back in the day have quickly realized that we weren't going to go beyond 4 gigahertz. We're now at 5 gigahertz, which is fancy, but CPUs are going wide. And what that means for everyone is that, well, we can't just throw everything onto a single core anymore, right? Even the folks yesterday from Age of Darkness were talking about doing a lot of parallelization and doing data-driven design and going back to the olden days of, like, was it plain old data and going down that route. And now these days we're making more games that are very much able to be parallelized. So, like, once again, Age of Darkness, they're doing all the stuff where you've got, like, many RTS units and all that. Even just generic tasks like save game systems. Ooh, spoiler alert. But sometimes you just need to do a task that you don't want to block the game thread. You want to let it run as quickly as possible, and you just dump it off onto a separate thread and go on your merry way, and then go, hey, when you're done, call back to me. So, why this talk? Because I have been into many, many studios, and the number of times I see people starting to, like, create a brand new thread and then, like, wait on that thing and have callbacks, not use the existing systems in the engine, is too damn high. So I want to try and change that and do a bit of a PSA talk. So in Unreal, there's actually a couple of threading systems. So they've been slowly adding them over time. Some of them are old, some of them are new. But we've also got features like Mass and PCG, which can do a lot of the pipelining stuff for the art side of things. Now, we're not going to talk about that today, so we're going to go right down into the deeper level and talk about how we can get your code to be multi-threaded. The systems that we're going to go over, as is mentioned, the runnable threads, async promises futures, thread pool, task graph, and task systems. Now, before you go into any kind of threading. It is an optimization problem. Solve your problem first. See if you actually need to optimize and do a profile before you do it, right? I've seen too many teams who go, "Oh yeah, let's go straight into the optimization route," because it is fun. Like, everybody loves optimization, right? Maybe. But the thing is that like sometimes that's not the best time to do it. Sometimes it is just good enough to get it out the door, get it working, and then do a retrospective and build your systems around it. Cool. So, without further ado, I'm going to race through this stuff because the demo is going to take quite a bit. But the first one off the block, we're going to go through a lot of the base systems that a lot of the engine is built on. So that's going to be runnable threads. So a lot of the stuff that's run in the engine is run off runnable threads, like your game thread, the render thread, the RHI thread. All of that is spun off by these runnable threads. And now they're great, and I've seen a lot of people going, "Oh yeah, let's spin them up and use them for short-term." That's not usually what they're used for. They're usually used for like engine lifetime or long lifetime threading jobs. So you want to use these things in a way that's like, all right, we handball a lot of work to them, like an audio thread or something like that, and they keep on polling and doing work throughout the lifetime of the entire engine. Yeah, creating them, because of that, creating them is expensive. Now, whenever you create any type of thread, sometimes, like, depending on your OS and all that stuff, it could take, like, literally 500, like, microseconds to actually spin that thread up. So it's quite expensive when you're like, hey, I want to do an optimization task, and then go, I'm going to create 50 threads, and before you know it, you got, like, 5-10 milliseconds just waiting on threads being allocated by the OS and spun up and all that. So there's better ways, which you'll see soon. Cool. So when you're making a runnable thread, actually, how do we... Ooh, oh, yes. All right, beautiful. So we've got this fRunnable, which is a class that's just it's an abstract class. We go in, implement it, and then in here, you just got to run. Now, there is like an exit function that you can implement and all that stuff for when you call an exit on the runnable, but you do all of your work here, and then just like a normal, like your main function in your hello world, if you remember that back in the day, returning 0 is like, yeah, success. Any other error will be like an error code of your choice, right? Now, when you want to spin these up, we create a runnable thread using the runnable thread, was it static? We can give it a name and then pass in our runnable work that we've created up here. And then that'll just spin up, take a little while to get off the ground, and then just go wild. Now, if we want, we can kill it. Sometimes we want to, sometimes we don't. Or we can just let this thing get to the end and then it'll automatically stop. But we always have to clean up. So be aware of that, because I'm sure that some people have been bitten by that in the past. Cool. So instead of doing runnable threads, why don't we just have a series of threads that are already pre-allocated? So this is what the thread pool is. So what happens is that at the start of the engine, we can create these ourselves, but at the start of the engine, there is actually like a global singleton that has this thread pool. It's called gthreadpool, which you can see. Yeah, here we go. So it starts up the engine, allocates like a number of threads based on the amount of logical cores that are in your system, and then basically puts it in this queuing system, which is part of the thread pool. And so whenever you need to use this thing, you can do like the frunnables, create a subclass of IQ'd work, so you implement the interface, do your work, create an abandon issue if you want, and then spin it off. So in this case, you can just do a loop. You could say, hey, how many on this thread pool, how many threads have been allocated to this thread pool? Oh, 32. I've got 32 cores. All right, sweet. Let's go wild, add as many jobs as possible, and then it will spin up pretty quickly because these things will just sit in the background and just idle and wait for jobs to be passed in. And the nice thing about that is that you're not paying the cost of creating new threads, and then it can just spin up super, super quickly. Now, there is another type of queued thread pool, which is this, and you can actually allocate your own versions, and that thing is basically just like a concurrency system. So you have a thread pool that gets allocated like 32 threads or 15 threads or how many that you've got in your system. And then you basically can just pile tasks on. And then as those tasks complete, it goes back to the queue and then pulls them off, and it'll only limit the max amount of tasks to the number of threads that have been allocated to it. And in fact, actually, that is what this singleton is set up using. It's just hidden behind the lower subclass. So yeah, cool. Now, async promises and futures. So there's a couple of little helper methods that access stuff like the thread pool and the other task systems that are in Unreal. So most of them are you can just include from async.h. But up here we've got async, and in here we can specify the type of async task it could be. So we could say, hey, instead of using the thread pool, let's use a runnable, which will actually create a brand new runnable thread for you. So it's kind of like a little convenience function for the many different threading solutions that are in the engine. But the nice thing is that it gives us promises and futures. So under the hood, it spins off a promise and then returns us a future. And if we want, we can just be like, oh, in a separate thread or even in our current thread, let's just wait for that when we call the future and then get. And that thing will wait in the background and then return the value that is returned from here. Now, we also have parallel for. Now, this is super sweet. It uses the thread pool under the hood. But basically what you can do is you can say, hey, I've got a bunch of data that I want to dump onto all of these threads. Here's the number of them, and then let's just use a concurrency-based thread pool to just run through all of that data. Then it runs this lambda, and through this array, for example, we can then access each index of that array and then do some work on that location. So that's literally just like, it just locks the current thread and then spins off onto, say if we've got 32 tasks that we need to run, it'll lock the current game thread and then spin off 31 threads separately. So that is super useful, and I use it all the time. Now, the last one is kind of similar to the async thing. So this is actually calling straight into the task graph, which I'll talk about soon. But the nice thing is that because the task graph is built in to the existing threading system and the threading framework, so knowing about like your game thread and your render thread, RHI thread, and all that stuff, you can actually specify, hey, I want to run this on the render thread, or I want to run this on the game thread, and stuff like that. And we'll get into it a little bit soon, because it means that we can do some cool stuff without having to lock. But spoiler alert. Cool. All right. Now, so if you've ever done any other kind of multithreading in any other application, even if it's like pthread or something like that, we've always got our base primitives. So we've got atomics. So the nice thing about atomics, if you don't know what those are, is that they effectively share state across multiple thread states. So between your caches and all that stuff that get duplicated, and it's effectively lock-free numbers, and I put that in quotes, still abstracted away from you, so they do have a cost. It's almost negligible these days on modern CPUs, but there is still a cost. But they are very useful for being able to sync up tasks between threads, so another spoiler alert. Now, we do have our generic locks, so we do have the normal mutex locks, which I try to avoid like the plague, but sometimes they are a necessary evil. So these things, when you run two thread locks at the same time that share the same section, then one of those jobs is going to be waiting for the other until that's done. And for optimization, that's not great, is it? Now, spin locks, on the other hand, so mutex locks are more of an OS feature. So it literally tells the OS, hey, I'm waiting, you can take me over for a while and do something. But that incurs a context switch, right? So the OS's scheduler will go in and go, oh, well, all right, cool. Well, I'll grab a task off you and just do something over here, and then I'll come back to you when I want. That's sometimes bad when you're wanting to do like really like low latency solutions, right? So that's where spinlock comes in. So spinlock, it literally does what's on the tin, sits there in a thread, it goes wait. It's a very hot wait, right? And then when it's done, it just exits and then continues on. So Now, and we also have synchronization events. So these things are super useful for being able to do stuff like synchronizing multiple threads and telling other threads like, hey, I've done a job, and then being able to wait in the background and then getting the call to say, continue on. So for example, we get a sync event, and in this case, we've got a pull system in the engine because we've got systems for stuff in an engine. And what you can do is you can call that off and then maybe deploy some form of async task and then wait in the current thread for that task to be done. And then in the other thread, we can then trigger that event, and that wait will not immediately, but practically immediately continue on. So it can then go on and do its thing. And that wait will return, if it has been triggered, a true state, but we can also specify a time limit. So if we go, actually, we only want to wait for at most like maybe half a second or something like that, then we can tell it to just continue on. It'll return false then. And then return true if it's triggered correctly. So you'll see that in action later on. And then at the end of it, when you have finished waiting and you've triggered and all that stuff, you want to return that sync event to the pool because otherwise you will get memory leaks. So yeah, always clean up your stuff. Cool. So now we have another cool feature that's part of Unreal is lock-free lists. So you're going to have a little bit more of a in-depth example of this later on. But for example, if we were to say have some jobs that run on a separate thread, but those jobs can only be run on the main thread, like the game thread, for example. We could just say, hey, get my queue, push a new task to it, and then in the game thread, we just spin this and wait for tasks to come through and then execute them on. And under the hood, the lock-free list is effectively a linked list of atomics. And what that means is that when you you push an event or push a function onto that list, then because it's atomics, it gets synchronized across all of the cores, and you know that you're not going to get race conditions, which is always the devil of threading in any kind of environment. And the cool thing is that that pop function is also using atomics to pop those tasks off. So you can keep on feeding the system to put work in and take work off. You don't even need to do this for just work. It could literally be for anything that you want. You could have data that you're processing. You just keep on feeding data, and then another thread keeps on reading that data and doing something to it, right? So you could do whatever you want to it. Now, the second rule of Threading Club, I've kind of touched on this a little bit earlier, is that I've seen too many people writing their systems. So stop it. Please look around the engine first. There's many, many instances of this, not just in threading, that I've seen in my travels around Australia and New Zealand and talking to people online. There's generally a system, unless, of course, you're implementing something that's very novel, then sure. Have a look in the engine first. There's probably something. So that leads us on to threading the systems. So the first one is task graph. And in fact, the majority of the engine is actually written on this. For example, the game thread under the hood is spun up and then uses task graph to kind of accept queued tasks. So I mentioned that lock-free pointer list under the hood. Task graph will have a lock-free pointer list that goes through and then executes work. So every now and then between your ticks, it'll go, oh, okay, well, I might have some jobs on the stack. Let's process some work for a little bit and then do something. So for example, you could be on the render thread or another thread and go, hey, game thread, do some work for me. And in this point, you can go, hey, let's spin up a task that does something and then run it only on the game thread, right? And then it'll come back. But the main power with task graph is that it's in the name. It's a graph. And what I mean by that is it is a directed acyclic graph. So if you've ever seen a Git repository where you're like branching and merging and getting everything coming back and out, and there's always a dependency leading in one direction, that's what you can do with this. So let's have a look. So for example, we've got this job setup that we want to do here. So we've got our init thread, and we want to spin off a couple of tasks, not just on the game thread, but the render thread and any other thread. And then at the end, we want to sync up when they're all done and then do a completion event, right? So let's go through that. So on the init job, we've got our spin up. We can run that immediately on any thread, right? So we could be from the game thread or anything, spin that up, and then from here, we can have a job that spins up on the game thread, but it depends on the init job. So when this fella has finished running, then it will only execute this. And as you can kind of see, the same goes for our render thread tasks. And then we can go and chain task or go wide or do whatever, right? And kind of like pre-allocate this kind of like schedule. So this on your main thread that's initializing this will run through this really quickly and just queue this up, and then it can go off and do whatever, right? And then this will go on its merry way and continue on and execute these 3 jobs in series, that in parallel. And then finally at the end of it, because we've got all of the last jobs of each stream as prerequisites, only then will this finished job then fire off and then kick off onto the game thread. So at that point, we could go, hey, blueprints, I've done my work. Thank you very much. Hand over to you. Let's do something else. Cool. Now, Task Graph has been around in the engine for a few years. And in UE 5.2, I think it was. I'm actually not 100% sure on that, but someone can correct me later on. Task System has been started to be written. So Task System is a slight improvement on Task Graph. It is still a little bit of a work in progress because there is, from my introspection or inspection of the code in the engine, it looks like that Task Graph is going to be superseded by this. And there's a few hints in the engine that I'll mention in a tick. But we can do effectively the exact same tasks. So like before, you've got the init jobs, the job 1, 2, and then a chain of jobs, and then finish your job. Now, the only thing is at the moment is that it doesn't directly hook into the game thread and the render thread and all that stuff. So this is just a general purpose task system for any of the pooled threads that are part of the global thread pool. So we can't just specify the game thread itself, but I'll show you in a tick how to get around that. But the cool thing about the task system is it's got a couple of primitives in there that help kind of schedule and line up these tasks and move them along in a more logical fashion. So we've got stuff like the job pipe. So instead of doing a dependency queuing, you can basically just say, hey, here's this job pipe, and then you can just dump tasks. So this could be like a singleton living somewhere. So for example, the save system in the engine actually uses this to do its queuing. So whenever you say save, load, delete, is this existing, it will just add a job to the pipe, and then the pipe will make sure to execute that in order. So super, super useful for like global task systems that you need to chain and not necessarily know what's going to be there or not in the future. So definitely use that when you can. Now, as I mentioned before, task system doesn't use, you can't specify, hey, run on the game thread. So we can actually use a bit of a feature of the task system, which is that under the hood, we've got sync events that are also treated like tasks. So whenever you create a task in Task Graph or Task System, you've got a job that gets returned, and then you use that as the dependency in the next job, right? We can do the same thing with synchronization events, which means that if you've got a completely disparate like function, so say if you're taking a screenshot, because this is actually part of the reason why I'm talking about this, is we had a system at Gameloft where we've got performance profiling data that we capture, and we needed to also capture snapshots of insights data and then send it to a remote server for us to be like, hey, flag, we're under like our max or our min FPS, someone look at this, right? But to give context, we also take a screenshot. So you've got two disparate systems that are getting spun off and doing their jobs, and then you have to synchronize at the end and then send them both at the same time as one event, right? And so for the task system, we could effectively just spin off, and then the screenshots don't support the task system. So we could use the task event to basically say, hey, spin off a screenshot, and then in the delegate that gets called back, we can call the trigger event on the sync event, and then because we've got this functionality to be able to nest features, so say conditionally you may go, hey, I'm going down this pipeline or this pipeline, you can just say this task now depends on that finishing or that finishing. And then whoever's depending on the parent task also has to wait for the child tasks. So whenever we're doing these screenshots and all that stuff, we can basically just say, hey, wait for the screenshot and wait for the insights data to be captured and written out onto disk and sent across, right? So it's pretty cool, pretty powerful. Now, I mentioned that there's hints of this task system becoming the de facto thing in the engine and superseding task graph. That is what this task graph new front end define is in the engine. So whenever you enable that, then you start getting access to a couple of enums that allow you to spin these jobs up onto the game thread and the render thread and all that stuff. Now, it hasn't been enabled, so I would say that it's still probably getting implemented by Epic. So here be dragons. Cool. So, and the nice thing about task system over for task graph is that we can enable the task channel in Insights, and it will show us fancy little connectors. So, we're going to get into the demo very, very soon because we only have about 15 minutes left. So let's get into it. So last year, who was at my talk last year? Put your hand up. Awesome, so we've got 50-50. All right, so last year I did a talk on serialization and save game systems and all that stuff. Now, I didn't have enough time to go into multi-threading, so I went, let's save some work. Save some work, he said, ha ha ha. And let's multi-thread that system. So under the hood, the save game system, when it was single-threaded, would go in, and now I've got a little key, and I just realized that I've got the key flipped. So flip that, so pink is save, and orange is load. Cool, that's what you don't do slides at 2 a.m., folks. Cool. So what we can do is we can go through, and when we're loading, we can decompress all of our data. We can go through the header, get any info on the map and all that stuff, and then load the map, and then wait for that job to complete, start storing actors, and then start serializing our actors. So we've got all of our save data, we want to load them up, yada, yada, yada. And then at the end of that, so for a load system, you might have the versioning data actually load in the front here, but for the sake of brevity of having this a little bit clearer, just in being nice and linear, it's there for now. But for saving, this is the exact format. And then at the end, if we're saving, we'll go through a compress step, and then that'll be written to disk, right? Cool. So what happens if we wanted to multi-thread this? So let's go. So we're in the game thread right now, and we can choose to go, you know what? Half this stuff we probably don't need to throw into the game thread because it's just a waste of time. And remember, threading doesn't always mean that you're doing everything faster. For the most part for games, the biggest crunch factor is the game thread being saturated and the render thread being saturated. So even if you're just taking jobs off that and you're adding latency, you're removing hitches and all that. So that's our main task for the first step. But this still might have, say, 10,000 actors or something like that that you're trying to iterate through and save their state, right? And that could take a long time. So let's go one step further. Let's decide to do a bit of serialization in parallel across multiple threads with the rest of the actors. So we're going to jump straight into that. Now, prepare, folks, because we have some code. All right, so let's go to the start. So some of you folks may remember a lot of the save game plugin. If you haven't seen this, there is code that is uploaded, so there will be a QR code at the end of the talk, so definitely access that and check it out. We've got two main functions. We've got a save and load function, and in each, it will go in and call a method to spin off a job to our save game pipe. The save game pipe being a part of the save game subsystem, and it will do our queue for us. So in here, we've got our serializer that we initialize, spin off a task to start the serializer. It will return a task and then have this task that's spun off have a dependency of the complete condition. So for example, you can see that we've got our insights regions starting up and ending, so it's nice and readable. We can see, oh, okay, when this callback is finished, we've done our job. We can print off, we can update insights, yada, yada, yada. But most of the magic happens in our do operation. So in here, I'll scroll this back down. So in here, we iterate through, we've got our main save system, we start spooling up our tasks. So as you remember, if we were loading, we would decompress our data. So we spin off a task separately onto any other thread just to start decompressing. And then after that, we have another task that will then start serializing our header information, our versioning information, but it depends on that decompression step prior. So once that decompression is done, we continue on, and so forth and so forth. So if we're loading, now we've got all of this header data which contains our map and what to load and what version info we've got. So like that screenshot mention I had before, the level loading system doesn't use task graph under the hood or task system or anything. So we've got no way to depend on it, on returning anything. So let's go forth and we start using our map load event triggers. So in here we can pass in a map load event, and then when the map, so we can kick off a map load, and then when the map load has completed, we can trigger an event. And then that event is now being used as the next task's dependency. So we're now going, okay, cool, we've gone to the game thread, let's load a world, and then let's just wait for it. We do nothing, we're not saturating the threads, we're just like literally waiting for the task system to get a call back saying, I'm done, cool. So we're saving time there. Meanwhile, while that's loading, it finally kicks back, and now we've got our serialization step that actually happens on the game thread. So for example, I've written a little helper, which was in the slides before, and that's this little execute on game thread helper, which is super, super useful. So that thing can return our tasks and kick them off and continue them on. And in here is where the real magic happens. So serialized destroyed actors is basically like over the lifetime of the save game, it will store whatever actors have destroyed themselves, right? So we just save out weak references or like soft object references to those systems. So whenever we are loading and there's destroyed actors, destroy them if they were in the map, right? So just destroy them straight up. And then only serialize the ones that are still around. So in our serialize actors step, so this is going to merge on to a little bit of thread safety. So now there is one big assumption in this that maybe some plucky eyes have noticed already, is that by default, most things in the engine aren't thread safe. There are a few exceptions, and there are a few tricks to kind of mitigate that. Now, for your projects, you want to, it's definitely per project, you might be using plugins that might be accessing UObjects in separate threads. It is up to you to vet whether or not your stuff is going to be thread safe. Without further ado, I'm going to continue on. So if you remember from our little graph that I showed before, we had the serialize actors method just go wide. It will start serializing many over many tasks. So in here, we've got a bit of a setup. So we've got the spawn IDs and stuff like that. So it's matching existing stuff that should, if it's spawned, it'll match them up with the new spawned actors. But we've got two jobs. We've got our initialize actor, which I'm going to go through very, very quickly, goes through, gets some initial data like the name of the actor, its class, and its spawn ID. Then under the hood, because not everything that we access on our actors can be thread safe or its data is thread safe, we actually have this little system that allows us to spin off a little job to a game thread. And because we have control of the game thread now, we can start using a queue that we may have mentioned before in the talk. So in here, this main job is going to do stuff like, oh, if we are a spawned actor, actually spawn the actor. And that stuff can only be done in the game thread, right? There's a couple of other tasks that need to be done for the actual serialization step, but for the most part, this initialization step isn't actually serializing any of the properties yet, because we need to initialize all of this to start setting up our redirect system. So, for example, if you have a brand new actor getting spawned and there's a conflicting name, then you've got to now, for the rest of your save game data, redirect that reference to that actor who has its name change. And that needs to be done in a single threaded context for the next step. The next step is then we've initialized our actors, they're all spun up, we've got them all in this actor data array, which is, where are we? Here we go. And this actor data array does something a little bit special compared to the other project, is that under the hood, it has its own serializer. It has its own separate data, and that means that we can start just ignoring having to do locks. We just spin up like, hey, we've got this many actors, and we'll serialize or save that data to its own little struct, and then at the very end, we do a merger step on the separate thread. So we can take off as much work off the game thread as possible. Let's keep going on that. All right, and then in this step, we've got the actual serialize. So this is the point where we start thinking about serializing the properties. Now, nice thing about serializing properties, especially with the serialize script properties function that I mentioned, which is this fella right here, is that it doesn't access any other U objects by default unless you tell it to do it. So it only goes in, it gets a U object reference, and it goes, well, all right, cool, let's serialize out the reference, and that's it. It doesn't dive in, which means that inherently it's thread safe. The main rule set that I have is whenever I want to thread save anything that's like a U object or anything like that, as long as it's self-contained and only doing work on itself and not getting access from anywhere else or accessing anything else, that's probably a pretty good bet. And I say pretty good bet because you could have other plugins that do that on you and you don't realize, but a pretty good bet that it's probably good to run on a separate thread. But sometimes, even inside of some of this data, there are things that you can't thread safe. So for example, whenever you do any kind of save game, when you load, right, maybe you get some velocity data that you now need to assign to your actor. So you've started shooting your gun, firing it around, and suddenly now, okay, now it's got to have a velocity assigned. Now, in some cases, like the positioning needs to be done on the game thread. Needs to be set there. You could get race conditions because like maybe something else is accessing that position of that actor at that point in time. So sometimes you need to spin that stuff up. So now we've got our queue system from before. So in here, we've got this colon serialize that can go through, and if we're not a thread safe actor for the purpose of our exposed blueprint function, then we can dump this off onto the game thread. Otherwise, go wild, just call it on the current thread. And now, let's go into this little thread-safe queue. So in here, we've got, really, Visual Studio. Sometimes I love you, sometimes I don't. Cool. So in here, we've got a couple of systems. So we've got our queue. So whenever we add a task, we push to a work queue, and then whenever we're waiting for that queue, we can process it. So we can go through, we can basically spin on that work queue, and when it's done, we've got a sync event that will wait, and if anything's added to that queue again, it will trigger the sync event, and then it will continue on the queue. And if then it times out, it goes to the end, tells us if we've done any work, and then we can do something. Now, back in our save game serializer, the way that we handle this is we've got this little helper called execute jobs. And it uses the concurrency limiter. Now, I haven't mentioned this yet, but the concurrency limiter is basically like, hey, maybe we've got a thread pool that the task system uses under the hood, and we have 10,000 jobs, but we only have 30 background workers to work on. So let's just feed the queue. Let's just put them on. They all run in parallel. It's not a full-on queue, but it is a work system that just pops and grabs the next job off the stack, kind of like the work queue that I mentioned before. And so through here, we can go through, and whatever job that we're passed in, it goes through all of our actors and then just executes. And when we've completed that stuff, then we can finish. But we do that only on a separate thread, but we are currently in the game thread queuing this stuff up, because while we're in the game thread, we have control over the game thread. No one else, we can assume, is going to be accessing our U objects. So that's kind of like the nice little special sauce of this system, because we're making sure that, or at least we're making the assumption that no one else is on the game thread doing stuff, because we have control of the game thread. So our objects aren't getting touched. So with that in mind, because we've got control of the game thread, we can then do that little process and wait for the queue. So anytime we have some job that comes from our serialization step that goes, hey, actually, I'm not thread safe, you should run me on the game thread. This is where that queue is resolved. So it will wait in the background and basically just pump that thread queue and basically just do all of the functions that are asked to it. Super, super powerful. So let's take a look at that. After that, there's the usual stuff of like, okay, actually, I will jump forwards, because once we've gone through all of that, if you remember, I mentioned we've got that actor array that's got all the actor info, and it's got all of the save data put into that actor info array. At the end, it will then do a merge step. So this, if we go back up here to the do operation, here we go. So we've completed our serialized actors. Now, if we're saving, we can merge our saved data. And in here, it's just a single-threaded operation that runs separately to the game thread. So remember, we're just trying to take off as much from the game thread as possible, so we're not hitching. So we get all of that data, and just in serial, we just go, here's a new array. Append, 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 append. Just keep on dumping that data. Make sure that it's structured properly. And along the way, we keep references to where the start of each actor is, because when we load that data, instead of having to go back in serial and read that data one after the other, in the load game on the threading side of things, we can just say, this actor is at this exact point. Let's just access that point in the array of data that we've just decompressed, and then just go full parallel as well. So everything when you're doing threading is just thinking architecturally about how do we access data without using locks. Because as soon as you start getting locks, you start getting potentials for race conditions and all of that nasty stuff that everybody hates threading for. Hence why we're using the task system. Because most of this stuff is like very clear definitions of here's a graph, here's what happens, this is the ordering, this is what kicks off when this is done. And it makes it so much easier for your mental load just to think about it that way. So we've got our merge save data, and then after that it goes through and it does the compression step, and then we can reverse that whole step and do the load. So let's have a look at that. So under the hood, we have our good old insight session running in the background. Let's spin up our actual demo. and check it out, because you've seen a lot of code and not a lot of pretty things, and I am sorry, I am a coder, so it's not very pretty. So in here, we've got our save game. We can hit F6, and I'm hitting F6 right now. You can't see any hitching, and we can hit load, and we've lost our pieces, right? Now, what happens if we go full overload and we say, oh my god, there's so many assets? I'm hitting F6 right now. I'm still hitting it a lot, and let's hit load. Hit load. Hit load. So, let's have a look at how that looks underneath in Insights itself. So, we've got, I've spun this up with the actual task channel. Come on, let's go. So we can see, here's our save step. So I've set up, in Insights, we've got a region that's been spun up. So we've got our save game. That's only taken 6.3 milliseconds. Do you want to know how much the only single-threaded method is in the last project? It's 150 milliseconds to do all of this. So we've literally got like a 20 times like improvement, almost like 25 times improvement. So under the hood, we've got all of our tasks. So save, we've got, oh yeah, bugger, I forgot to enable the stat named events. Actually, I'll do that quickly right now. We'll do a quick test. So under the hood, pro tip, whenever you're setting up any of your Insights data, put this little tag on the end, and that's when you'll get all of your extra little events from the scope cycle counter and all that stuff. So pro tip, it's good. It's very, very good. So let's dump this out again. So let's pick up gun, do the quick little save, and then let's do the big save, and then reload and close, and let's check Insights. So I now realized the 6 millisecond was actually the short save. So we've got the short save of 6 milliseconds, which is only 19, so the longest save is 75 milliseconds. Now, for reference, 75 milliseconds from the start of the process to the very end of the process. Now, the actual game thread side of things is only 14.8 milliseconds. So if we're saying that the old game system, which is only purely single-threaded, was 150 milliseconds, now we're doing 10 times quicker, which is awesome. So we've got our two steps. We've got our initialize actors. So when I double-click this, we can start seeing, hey, there's this like little task that spins off, and oh, which one is this? Oh, that's the serialize header. Let's double click that guy. What does that depend on? Ah, there's another execute task. What does that depend from? Oh, that's from the save event. That's pretty cool, right? Now, like back in the day, you just never had this data. If you ever used front end, you're just like, I don't know what called this thread. In the task system, we now have that dependency information, which is amazing. Now, the next thing as well is like, check this out. So we've got all of our initialize actor tasks that are spinning off, and what I haven't told you is that there's 10,000 actors being serialized right now. Just save, all multi-threaded. So let's go to the actual juicy part of the serialization part, which is the save game serialize method. This isn't my updated version. That's a shame. Here we go. So here's where all the actual unserialized events go, and it just goes as wide as possibly can be. So you can see how we're gaining all of this back, right? It's just coming back in, going wide, stuffing as much as we can, and as short of a time possible. And then for the load, we're doing effectively the same thing in reverse. Now, the load's a bit different because obviously we're reloading the entire map. So it's going to take 1.1 seconds, but that's because we've got all of these spawns that need to happen. All those, like literally 10,000 of the 10,019 actors are spawned actors, and they can only be done on the game thread. So we do still have to pay the cost of the game thread in certain contexts, but if you really design your game well and you're not using spawned actors at all, you could cut a lot of that stuff. So yeah, maybe don't do that, but it depends on your game. Cool. And now you may be asking, like, but Alex, like, blueprints, how are you saving that and getting custom data out and handling all of that stuff? Well, good thing you asked, folks, because there is one little node that I've put in here that allows us to kick work off from a blueprint system into the game thread work queue that we've created. So in here, we've got our, these are the main things that are mass parallelized. The rest of it is just single threaded. So in here, if you remember from my talk last year, for the people who were here, we've got, oh, give me a tick, sorry, that is the wrong project. All right, I'll wrap this up because I've only got a couple of minutes and then we'll take a couple of questions. So we've got our main task, right? So in here, I've put, this is a contract. So if you sign this contract, it's on you to follow it through. So what happens is that, like, we can then basically tell myself, hey, is this actor thread safe? And then the programmer has to make sure that that actual blueprint and the data that's being serialized is thread safe. And to do part of this, we've got a couple of functions. So we've got the serialized actor transform, which under the hood actually under pressure. Under here, the serialized actor transform reading is perfectly fine to read off any thread in Unreal. And plus, because we've got control of the game thread, nothing else is acting on that actor at that point that we're reading. So assuming none of the rest of your actors are accessing that actor as well, then we can just read that data out. So saving, we can just get the actor transform, serialize, and then be on your merry way, right? But on loading, we need to set actor transform, which actually fire off like overlap events and stuff like that. So under what we do is we've got this lambda that goes in and we say if we're in the game thread, yep, we're cool. If we're not, do it up. Pretty cool, right? And we can see that inside of our actual insight session. So in here, process thread queue, and we've got our spawn actors, and then in between every now and then, we've got our set actor transforms. So that gets dumped off onto the game thread, does the job, and then goes on its merry way. And it's a little bit asynchronous, but it's done in order, which is cool. Now, the other thing is that, what about for stuff that isn't able to be accessed? What happens if you're a blueprint-only programmer and you go, I want to run something on the game thread? How do you do that? Well, I've made a custom node. So anytime you go in and you say, hey, do something, and then append score game thread on this one node, and we do something like set actor transform. So we're just going to redo what we were doing before. And I can use mice, I swear, thank you. Under here, what we can do is we can just say game thread, do something on the game thread itself. And so under this, what it does is, and I may as well go through this, is it grabs data that's passed into here, puts it into some plain old data, takes it into a custom little node setup under the hood as part of the expansion span of Kismet. I really want to do a talk on this because it's cool. Nick Farrar, what I'm talking about. If he's maybe not. Anyway, but under the hood, we've got this custom node that will then fire off an event that is in our save game function library, and this save game function library takes some custom data, makes a lambda, and then spins that off onto the queued game thread. And it's just basically looks like a normal function. You just palm it off, and then your blueprint is fine. Whoever who's using the save game just goes, cool, now it's relatively thread safe. As long as they understand, don't do cross objects. So good. And yeah, that's pretty much it. So we have maybe a few questions. Didn't have any. Cool. I like this. Load this up quickly. So remember, blueprints aren't threads aren't the default. I've got functionality for that. Check it out. object, new objects, but default contract beyond it. Thread also spread the trans out them out. Summary ways many threading, do threading, thread safety possible is be wary though, here be dragons. And task system is highly flexible, but if you're doing long term stuff, do it in F1 thread. Cool.